Hello, everyone. Good morning, good afternoon, good evening from me as well. I'm Guilherme Martinez Roura from the International Telecommunication Union, and I would like to welcome you all for joining us today AI for Good webinar on sustainable robots. What does it take for a robot to be sustainable? This session is part of the AI for Good robotics programming track, exploring how AI-powered robots are helping to unlock our human potential and advance the United Nations Sustainable Development Goals. We have a distinguished set of panelists today, but as always, we're counting on you, the participants, to help create a very interactive session. And without further ado, I would like to introduce our moderator today. His name is Fiacra O'Brolchain, and he's a Marie Curie Research Fellow at the Dublin City University's School of Theology, Philosophy, and Music. Fiacra, welcome, and the floor is all yours.
Thank you, Guillaume, and thank you all for inviting me. As Guillaume mentioned, my name is Fiacra O'Brolchain. I'm a philosopher at Dublin City University in Ireland. I focus mainly on applied ethics, environmental ethics, and the ethics of technology. I have an interest in both robotics and the Sustainable Development Goals. So I'm delighted to be moderating this extremely exciting panel discussion today. I mean, this is such an interesting panel discussion because amongst the biggest challenges humanity is facing today are those relating to our impact on the environment and those relating to the rapid pace of technological change. And it's great to see our panelists discussing positive ways that technological change can help us deal with some of the environmental challenges we're facing. So we have 4 extremely interesting talks from people who are actively involved in working on robots or robotic systems that can assist with the realization of the Sustainable Development Goals. And they are Mr. Damien Sall, the Coordinator of Robotics and Automation at Technalia, Dr. Liu Wang, Professor and Chair of Sustainable Manufacturing at KTH, Mr. Poldi Heydrich, who's the Manager of Automotive Market Segment at KUKA, and Ms. Gayatri Manakuti, the Haptics and Robotics Research Coordinator at Amachi Labs. So without further ado, I will moderate and I will ask some questions at the end, but of course, I'd be delighted if the audience have lots of questions, as I'm sure you will. So without further ado, I'll introduce Mr. Damien Sall, Coordinator of Robotics and Automation at Technalia. Damien?
Yes, thank you. Good morning, everybody. Good afternoon, everybody. So I'm Damien Sall. I'm a researcher in robotics at Technalia in Spain. And today, what we'll talk together is some activities that we are doing in sustainable developments and the use of robots in these activities. So Technalia is a research center in Spain. We do applied research. We are about 1,500 people. And the goal that we have is develop technology and transfer it to the society and to companies to transform this technological research into prosperity. In terms of robotics, we're about 80 people, and we deal with all these kind of systems that have wheels, that have arms, that fly, that go on the water. If you want more insights, you can Google Technalia robotics success stories, and you'll have a few videos of extracts of some of the projects we do. But today we're going to focus on sustainability in terms of environment impact. Okay, as you know, we are putting lots of stress on our planet as a human species. We've already passed 6 of the 9 limits, and I won't come into the different solutions that there are. But let's say that first we should try to do less sobriety. We should prepare and anticipate. That's called the resilience. And then as engineers, we can also work on something that should be the efficiency, do better with what we have. And in that term, in terms of robotics, what we have decided in Technalia to focus on is on the circular economy. So the question is, can we do something? And that's the kind of question that we developed a few years ago to develop this circular robotics initiative. And we focus it on circular economy. Circular economy, it has an impact on the CO2 and the material extraction. And in terms of technology, in terms of robotics, it appears to be an alternative where we can have an impact also. So I can't do anything about gasoline of cars, but I could do something about circular economy with robots. This propose to have some impact on various of the goals of sustainable development. And the claim that we have here is that when you look at circular economy, today there's lots of hurdles to be faced, such as the price, the quality. There's a lack of trust and traceability between the agents. Sometimes lots of inefficiencies. And on the other hand, robotics, it has proven to be a champion at cost killing, constant quality, guaranteed traceability in the linear economy. So what we want to do is that we think that we can transfer these benefits also to the circular economy, and that's what we're trying to do. So I'm trying to get you engaged in it, and let's fight for it together. Alone, we're no one, but together we can do something. So for that, in this internal strategy, we have developed 4 lines that we try to develop with research projects. Some of them are funded by the European Union, others are internal projects or funded by companies. And we have defined these 4 lines. One on the removal of waste from the environment, sorting and classification of the different waste. Then a line on dismantling of equipment before their recycling, and a line on inspection and repair. So we don't cover the 9 R's of the circular economy, but we try to identify where we can have impact. We're going to see today 3 of them, and then conclude with a few comments on the impact of these things also. So the first one is this robot that is called a cable robot. As you see, there's cables hanging from the platform to different posts. It's placed on a floating platform, and we are developing it in a setup in Venice, where we remove the marine litter, so the plastics, the weights, the tires that lie on the seabed of the lagoons. As you can see here, there's a tire that we are collecting. We use bathymetry and AI with cameras. It's teleoperated. It also has automated motions. And so that's one solution to remove this litter from the seabed and removing these plastics from the environment. Other alternatives, they usually do things on the surface, on the floating plastics. And we decided to go to the bottom. So we just released today this nice video. If you Google that Maelstrom seabed cleaning platform, you're going to see a complete video that you have also the link here. The next line is to classify the waste and sort them. So if you go to plants that manage your waste, there are lots of machines, automated machines. There are already some robots, but they focus usually on the household packaging items. What we want to do here is to develop these capabilities for other streams. Streams that are not treated so much today. So the plastics in the marine litter. We also work on construction waste. These are 2 EU projects that we have ongoing, Recordmatic and Maelstrom. We also want to do that on electronics, on textile. The idea is really to have an AI that we train with 2D cameras, 3D cameras, multispectral images to understand what is the material of each waste item, to classify it, and then put it in different bins so that then we can have a specific recycling process for each of them. The third line that we do is on robotics for disassembly, dismantling, deconstruction. Here the idea is that before this phase of sorting that we just saw, there's lots of components that are made of multiple material that are screwed together, that are glued together. And if you just break them and try to sort them, it's difficult, and you don't have achieve a very good purity in the process. So what we want to do is use the robots that are agile, that are smart, to be able to disassemble these items, to dismantle them prior to their recycling. And here again, we want to target things as batteries, electric motors, electronic devices, textile again, building components, whatever needs to be dismantled, separated nice before so that we can recycle before. And the target, the issue here is the complexity. There's lots of different variants, lots of different conditions. Products come from a very long time ago where you don't have the reference. It's not like in a production line, you don't know what you have. So it's called a high mix, low volume scenario. And here again, in the linear economy, you have example of a project that we do on the right. We already do that with robots, with small quantities of products, high variety of parts. And this AI, this robotics autonomy, we want to deploy it on the circular economy. And so we have already a few projects starting on that for the battery dismantling, for example. And that's something that we need to keep pushing, okay? So all this is very nice. This is using robots to do things for the environment, for the circular economy, but it's a big technology, and we put new technology, new sensors, new AI. So is there something that we can do also in robotics to impact less? The answer should be yes. Our next speaker from KUKA will also give you insights on that. Robots are complex machines, they are electrical machines, so we can improve them both in terms of energy use or in terms of design, eco-design, paying attention to the materials that we use. That should be only one single material, not very complex ones, and do something on the machine by itself. But we do put technology on the environment, on the planet, and we should at least know whether the impact of this technology is very high or very low. That's something that we are starting to do in these projects. Trying to think about what's the CO2 impact of these smart AI-boosted agile robots. Usually you do that using a life cycle analysis process where you estimate the production, the use, and the end-of-life cost of these technologies. And we've tried to do that, we started to do that, but it's very difficult to estimate because of the databases that exist that are very good for metals and materials, but in terms of electronics, sensors, cloud, everything that is now related to the AI, the cloud, the computation, there's not so much reference for that. So it's something that as a community we should do together with the people that make these evaluations of environmental impact. It should be used for me in all these projects, or even as a general idea when you put technologies on the market to assess really the cost benefit in terms not only of euros or dollars, but also in terms of environmental aspects. It's not so easy, but at least try. I engage you to start doing one of these processes, to sit, to think and evaluate. And even if it's not complete or perfect, it keeps you in a good mind bending in the reflection or meaning of what you are putting as a technology. So that's it for me as an introduction. Thanks a lot for the attention. You got my contact if you want to discuss that further. And I'm now leaving the floor to the next speaker. Thanks a lot.
Thank you very much, Damien. That was fascinating. And so now we're going to move to Poldo Heidrich. I think so. Poldo, over to you. Poldi, pardon.
Okay, then welcome and thanks for the introduction. My name is Poldi Heidrich. I work at KUKA Robotics in Germany, Augsburg, and I'm going to try to take you on a short excursus on energy efficiency, and how can we use AI to increase energy efficiency in robotics. So first, robotics can tackle several of our sustainable development goals. And the first question is, what does it actually take to make a robot sustainable? Well, the simple answer to the question could be make it more green. And I'm not talking about the paint, I'm talking about where can we increase energy consumption, where can we decrease material usage, and so on. So if we have a look into the life cycle of a typical industrial robot, it is produced in facilities like at ours in Augsburg, Germany. So this is where actually the life cycle of the robot starts. Then the robot is transferred to the virtual world, where we do planning and programming of our robots. We plan our robot cells, our production, and everything. And this is then transferred to the real production lines, where our robots are producing cars, mobile phones, any kind of products. And now we're in a kind of life cycle, because our robots, they are multi-purpose machines, so they will be reused for different purposes. So when at some point we find out that, okay, let's stop producing this type of car and go on to the next, or the same with mobile phones or any kind of products, robots are highly valid to be reused in production. At some point in time, even the best products will come to an end of life. And at this point, robots are already very material efficient, because as of right now, we're able to recycle up to 98% of the material used in the robot itself to be recycled and reused for different things. So if we then try to get into, okay, how can we actually increase the efficiency, reduce our CO2 footprint or whatever goals? First of all, we need to identify what are areas that we can actually achieve something, because it doesn't really help if you go from 99.8 to 99.9% if there's a lot more ground actually to find. So is there a valid measure to find out sustainability? Can we somehow measure it at a robot? It's kind of hard. But we can measure another thing, and that is cost. And cost is always related in some point to CO2 footprint, material usage, energy usage, and so on. So if you have a look into the actual TCO, so the total cost of ownership from the point where you decided you will buy a robot, then use it for a certain amount of time, and then at some point discard of it, recycle it, or whatever. If you add up any cost, every cent, dollar, or whatever currency you use that you actually spend on that robot, you will find out that about 1/3 of it will be your initial invest. Another third will be its total energy costs. We took 15 cents per kilowatt for this calculations. That will depend and vary on your region and on your price that you pay in your industry. But this actually tells us, hey, energy is a huge factor in the overall total cost of ownership, and therefore also plays a huge part in the part of efficiency. Where can we increase or get better at the whole thought of sustainability within robotics? And we have to take this with a grain of salt, because there is no real one-to-one correlation between cost and sustainability, but it gives us a certain link. So if we look back into the slide I showed before, we asked ourselves the question, okay, this is a presentation for the AI for Good Summit, and we asked, okay, where can we actually try to get AI into this? Where can AI actually help us to increase, to improve? And this is quite simple, mostly in the phase of planning and programming. Because in the phase of we produce a robot, AI can help to some degree, but not too much. So the biggest potential is in the planning and programming phase. And I've brought 3 examples right now where we can actually increase our efficiency or avoid errors that are done in the planning and programming phase that have a huge impact on our energy consumption of the robots. The first is super simple and has nothing to do with AI, but will give you a short overview about how heavy the impact of simple errors can be. And the question is, pick the right robot for the right task. The second example I brought is robot placement in relation to its working area. And the third will go about motion. So first, I brought just a small chart. Here we see 3 different types of robots that can handle the various range of 60 to 210 kilograms. And they're all tasked with the same job to move an object of 50 kilogram. And as you can see, the energy consumption or the energy requirement to move the same object over the same distance with 3 different kind of robots, actually, it varies up to the factor of 2. So just reusing a robot because you have it in stock isn't the solution. So always try to not oversize your robot, try not to oversize your tools, because the energy consumption of a bigger machine will very, very soon outweigh the energy costs. But at this point, no AI involved. So let's try to pick another example where AI actually matters or can do something. What you see here is a diagram that shows the energy consumption of a robot that does a simple adapt, pick and place cycle. And at this point, we shifted the robot's position in comparison to the starting point of the adapt cycle by 10 centimeters in all 3 dimensions, and then measured how much energy did it consume over these cycles, to actually find out how big is the impact of the robot placement compared to its working area. And what we found out was staggering, because at this point we've seen that it will do up to a factor of 3 if you have a good or a bad position. In this example, what you see here, those two numbers, where's my mouse here? Those two numbers, you can see we shifted the robot by about 50 centimeters and changed the energy consumption by over 30%. And this is something that can be easily done in simulation, because there are ways to find out the energy requirements of a robot or a robot's movement and trajectory in the virtual world. So you don't need the real robot yet and do the movement and measure it. You can already have all those informations available in your simulation. So the key question is, at this point, for our line builders and guys who are planning the cells, try to not only find a position of the robot where he can actually do his task, but where he can do his task in an energy efficient way. And this is a new dimension that we need to address, we need to find. So this is one thing where AI could really help in the simulation world to find ideal positions of a robot in comparison to his working area. And the third example I brought to you today is an example of motion. We took a average production program, simplified it in a little bit. Now I would try to show you what usually happens in robot movement. A production cycle starts, and first the robot waits for the part to enter his cell. Then he approaches the part, then he decelerates again, waits until he gets a signal from a PLC, then moves closer to the part, waits for another robot to do something, then moves to his process point. Then he does his actual process, which can be anything, gluing, welding, whatever. And once he's done, he moves back to home. So what we see here is always the acceleration diagrams. So we can see there's a lot of energy used to accelerate the robot and a lot of energy burned to decelerate it. If the robot does this cycle for 10, 20, 50, 100 times, he should have the intelligence to find out, hey, dear user, I'm always waiting here, I'm always waiting there, and I'm always waiting there. But at the end of the time point, you always want me to be at this point in space at that point in time. I could move a lot more energy efficient if I didn't need to wait for 10 different other things, if I could just start slowly and move to my final position slowly and be there just in time. And this is something that is currently not as good as it could be. And this is something where AI could really help us in the overall motion planning and the generation of trajectories of robots. So I'm done, and I would like to hand over then to our next speaker.
Thank you very much, Polly. That was fascinating. And so now we are going to hear from Dr. Lihu Wang, who is the Professor and Chair of Sustainable Manufacture at KTH. So over to you, Lihu.
Thank you. Thank you for the introduction. So today I wanted to change the perspective, talk about human-robot collaboration and how this can contribute to a better sustainable working environment. And this can contribute to the SDG goals 3, 5, 9, and 12 as listed on top of this slide. So here you can see why we need to use AI combined with human-robot collaboration. In short, is HRC. I will use it frequently. The first one is relevance. If we consider the manufacturing shop floor in assembly operation, normally assembly, especially the final assembly of a car or aircraft, is very complex, and lots of decisions needed to be made. And most of operation cannot be readily done by automation because human judgment is still needed. In that case, if we use AI and HRC, it can fill the gap and bring the power of artificial intelligence with the power of human intelligence together. And the importance is listed here because the assembly through HRC can really lead to a sustainable environment for the workers on shop floor. It also has a broad industrial base. Many robotic makers have supported human-robot collaboration through the new brand of different type of collaborative robots. For example, from KUKA, just mentioned, ABB, Fanuc, Rethink Robotics, Universal Robots. They all support this movement towards a sustainable goal. It is also important if we use AI and HRC to help human operators, no matter the gender, race, physical conditions, and the skill levels of different operators. Eventually, with the support of AI HRC, every worker can do the same quality job and in a sustainable environment. However, there's a number of challenges that we really need to look into and try to resolve them. They listed some challenges here, how to address the safety issue of a human operator, privacy issue, when human operator need to reveal lots of privacy information to the computer system in order to guarantee the human safety and so on. And another challenge is the lack of standards when different systems work together. And the ethical issue is something else, that how to put this in practice is really a challenge. But why we need to have a human-robot collaboration that I mentioned earlier, robot can be used to help human, assist human instead of replace a human. That's the aim for HRC. Initially, robot may not have knowledge or experience, but learning from the experience of the operators through AI algorithm, gradually, robot will know how to do the job properly from the skilled operators. Normally, we use pre-generated control code to control robot. However, in a setting of HRC, everything is dynamic. We're in a dynamic environment. Generating code in real time is really challenging, but perhaps we can use a different modality to communicate and control robot. The natural way to the human is to use voice to control the robot, or use gestures. We use a haptic-based approach. There's another way to control the robot is to use human brainwaves. All the gestures, speech, and so on is controlled by the human brain. If we can retrieve the true thoughts in our head in the form of brainwaves converted to the control command, we can control the robot directly. So there's a number of different data already available on the shop floor from the hardware, from the robot, and the different computer systems. If those data can be collected through sensors, through robot controllers, through some smart tools, or even from a historical database, the data can be passed to an AI engine for processing to convert data into knowledge. Eventually, knowledge can be used in some domain-specific applications, in this case, HRC. What assembly parts can be recognized while the human operator is holding it, and what would be the human action in the next few seconds. So this action recognition is another topic, or the motion prediction in the next 5 seconds. Eventually, this AI-powered system can help robot to assist the human operator to do the assembly operation. HRC is quite broad. Here, I wanted to summarize 5 different topic areas. The first one we need to consider is human safety. This is R1, as listed also as the bottom red area. The second one, once the human safety is guaranteed, how to plan the robotic task, assembly sequence, and so on. That's another research topic. Then how to control the robot, R3, use an adaptive way, as I mentioned earlier, in different modality, is a research challenge. And eventually, how to support operators, use different modalities like augmented reality, digital twins, and so on. Eventually, everything needed to be supported by a smart sensor network in the middle. And this can really provide data and information for us to recognize different situations and make decisions adaptively. The first part, if we wanted to make humans safe in a robotic environment, we can use a different method, combine them together. Robot perhaps can be monitored, use sensor data mounted on the different joints or from the robot controllers to retrieve the robot control command. Everything is predictable inside of a controller. However, the human's movement is not predictable. Human can move suddenly, but if we install some vision cameras, we can capture the movement of a human and then put this point cloud of a human operator into the computer environment. The computer already have a model of the robot, and we can calculate relative distance in the virtual world. Based on the relative distance, we can change the behavior of a robot to slow it down or change it to different direction, modify the trajectory. It is also possible. So here I show you a recorded demo. To your right is image processing. There's 2 cameras to show the color images, and the color represents the depth information. The red is closer to the human and the blue is further away. After removing the background, we can only have the human operators from 2 different camera views, put them together into point cloud and calculate the relative distance as shown in the recorded demo to the left. Without touching the robot, it is possible to change the behavior or the movement of the robot, as you can see from the video images here. We can also use a deep learning algorithm to figure out what human operator is holding in the hand and what action he is taking. This can be done through the AI algorithm, as you can see here. The blue line and the green line shows different actions, a different part once the human is taking assembly operations. This is done in real time. So with this help, it is possible for the robot to take actions as well. So here shows robot can sense the environment, knows the trajectory of a human operator in the next few seconds, and hand over the parts at the right location at the right time. This is also called a context awareness in an assembly environment. So each time the human operator's hand has a different height. It can be captured by the camera and pass the control command to the robot. Another topic I wanted to share with you is how to control the robot through our brain. Use the brainwave. Brainwave can be captured by electrode, and the signal is passed on to the computer for processing, retrieve the command patterns, and eventually send it to so-called function block, and the function block is used to control the robot directly. If we think about a control command, normally it consists of 3 parts: the subject, a predicate, and object, as shown in the color here. And then this can be retrieved in a waveform in the time domain. Then we can convert it to images in the time frequency domain through a continuous wavelet transform. And these images are passed to the CNN, convolutional neural network, for processing. Eventually, we can retrieve the control command we thought silently in our brain is a robot place a cylinder, in this case, a cylinder head, and then convert it to function block to generate a control trajectory, and so on, eventually control the motor of a robot. So that's the way. Here captures the processing process. The last part, I wanted to show you another recorded demo to integrate different modality together.
To enhance the scope of robot applications in all industries, we need a new generation of intelligent robot systems that offer a truly symbiotic collaboration between human workers and robots. A system that not just guarantees the safety of human workers in a fenceless, dynamic and intuitive working environment, but also supports the worker by offering instructions and help according to the workflow. A truly collaborative robot system must also offer easy and intuitive tools for system interaction and robot control.
Symbiotic, show me the part.
Besides the collaborative aspects, a symbiotic robot system also needs simplified methods of robot programming, so that even non-expert users can easily create new program sequences or complex task planning, even for small lot sizes. Therefore, 15 research centers, universities and companies from all over Europe have joined forces in the Symbiotic consortium to develop new solutions for a safe, robust and reliable human-robot collaboration.
So I will stop here and look forward to discuss with you during the Q&A session. Thank you. So I will pass on to the next speaker.
Thank you very much, Li Huang. That was fascinating. Lots of food for thought there. So now we'll go on to our next speaker, Miss Gayatri Manikuti, I hope I've pronounced that right, who's the Haptics and Robotics Research Coordinator at Amachi Labs. So over to you, Gayatri.
Hi, thank you so much. Okay. So I am Gayatri Manikuti, and I am from Amachi Labs, Amrita Vishwa Vidyapeetham. Amachi Labs is a computer-human interaction research center situated in Kerala in India. So today I'll be talking very briefly about our work and specifically a specific case study regarding how we designed the robot to meet community needs. So at Amachi Labs, our main focus is on skill development, and we work on developing simulators, haptic simulators for vocational life skill training. In our work in villages, we also work on developing rural technologies and humanitarian technologies using robotics and wearables to bring the most intuitive way of working with modern technology to benefit the people in India. So for example, these are two haptic simulators that we have custom built in our research center here. The Apta simulator is a 4-degree of freedom simulator that can train a person with 19 different tools. And the bar bending simulator is a simulator that we built where the workers can learn how to do construction rebar bending. So the kind of people we work with are the underprivileged, the bottom of the pyramid that we typically see in the villages of India. So today, I'll be talking about specifically one work that we did, which is on designing social robots for the United Nations Sustainable Development Goals, SDG 3 and 6, based on community needs. So let me take you back a little to the year 2000. Ending open defecation worldwide is one of the key sustainable goals across the world. So in the year 2000, India initiated a massive campaign, community-led sanitation campaign. And yet, in 2014, about 70% of rural population in India continued to defecate in open. This is when Amachi Labs received a project from the United Nations Democracy Fund on how we can use community mobilization, capacity building, skill development, and sustainability maintenance for a community-led total sanitation approach using innovative methods. So, as important as it was to build toilets using innovative methods, we also found that it was equally important to spread awareness about the sanitation and hygiene, the microbial contamination of potable water stemming from lack of hygiene practices. This need that we saw in the community, based on the work that we did on a toilet building project, is what led to us to first build our first robot for promoting hand washing behavior change. Hand washing is a very simple practice, yet there are so many research studies which have shown that effective hand washing is not being practiced widely to contain the spread of germs. So we decided that we'll build a robot for hand washing, right? Working on two specific targets, the SDG 3.2 and 3.3 and SDG target 6.1 and 6.2. So what we did differently was, instead of focusing on hand washing behavior change using fear of disease and epidemics, our focus in this effort was to use robots which could provide motivation, positive emotion, and habit formation through positive persuasion. We worked with children because we found that children find interaction with physical robots very enjoyable, and a robot could repeatedly give nudges over extended period of time. Not just that, when we intervened at a very young age, children quickly learned to develop this as a habit, and then they took it back home and made this a community practice. Now, children became the change agents where we could affect a community change, right? And we could also maximize the impact by tailoring the robots to the needs of the community. And I'll come back to it with some examples on what we did. Besides this, there is also the fact that anything that we develop through such a research could be more widely extended towards other SDGs as well. So we began our effort with a Wizard of Oz experiment in a rural school in India with a social robot named Pepe. Now, what we found was Pepe was a very simple robot that was manually controlled, and we used it in a school for 6 days. And in our interventions, we found that the number of hands washed, that is just looking at the number of children who wash their hands properly, jumped 40%. Now, mind you, I began this talk by saying that a lot of the 70% of the interventions fail. And here with the robot, even with just a 3-day intervention, we saw a 40% jump in the actual hand washing. And after 3 days, even after we removed the robot and measured the quality of hand washing 1 week after the intervention, we still found that it was about 20% over where we began. This clearly shows that robots have a really significant way to make a positive impact, and that too a lasting impact on the community's behavior towards hygiene. And because of these positive results, we started our work to build a social robot for hand washing behavior change. Now, we base this design of our robot on the 3 sustainability principles: the social, environmental, and economic, because we believe that balancing these is critical for ensuring sustainability of robots. Now, what are the challenges we faced when we tried to use this? As you all know, India is a very diverse country and it has a very rich cultural heritage, right? But also, Indians have a very varying attitude towards technology, including AI and robotics. We did a teacher training intervention to teach teachers about AI, but we found that there was very poor belief states of the teachers in the potential of AI. Even though they were training students on AI, they themselves did not believe in the potential of AI. And there was also a diminished interest to explore innovative approaches in the classroom, such as introducing robots, right? This is one problem. The second problem is on affordability. For a country like India, one of the critical challenges we have is keep it low cost, to keep it affordable. Almost the price of robots have to be under $1,000 in order to really be something that can be scaled. The third thing is that for many of the social problems that we see in India, we have to tailor the robots to meet the diverse needs in terms of language, dialects, literacy levels, cultural diversity. And all this requires a very deep understanding of the local context and the user needs, and also the principles of the user-centered design, right? So the human-robot interaction has to be customized to accommodate to the cultural norms and the social expectations of India, such as responding to Indian names, Indian greetings, cultural customs in an appropriate manner. Also, if we have complex robots deployed in villages of India, there aren't enough skilled workers who are available to really operate them. Therefore, the robots that we built had to be very intuitive, almost like a button press or a voice control command operated robots. Then there is the challenge of gender norms. India has very complex social norms around gender, which influence the development and adoption of robots. For instance, we did an HRI study with an unmanned ground vehicle, right? This vehicle looked like a car and it spoke in a man's voice, it spoke in a male voice. And what we used the robot was to go and fetch water from a water tank to a village household, right? So the robot was shaped like a car, it spoke in a male voice, and yet when we asked the villagers, what is the gender of this robot? They invariably said it's a female. That's surprising, isn't it? And that's because the villagers associated the gender of the robot to the task the robot is performing and not on its appearance or on its interaction. Such knowledge, such nuances becomes very important in order to be able to develop robots that are acceptable to the people according to their own belief systems. So, we designed Hakshi as a minimalist social robot that integrates both audio-visual perception with artificial intelligence to nurture positive behavior change. And also, we co-designed this robot with children so that it can be done in a manner that is most intuitive for the children and the teachers to be able to operate, right? So we built in vernacular language capabilities into the robot, affecting computing capabilities, hand washing action recognition capabilities, and we custom trained the conversation agent so that it can work with Indian dialects. So this is the co-design process that we did with the children. It was a 5-step co-design process. And the idea here was to get a thick description from the children on what they see as the need of a hand washing robot. So the children actually built various robots. These are some of the robots the children built in the participatory design process. And they described to us what they wanted to see as the robot performing. And based on the insights that we got, we custom designed the robot. Right? So here is Hakshi robot that can engage with children. As you can see, we kept its design very simple. We just have an LCD screen as its face. Its internal mechanisms are very, very minimalistic. And the idea was that it can engage the children in the conversation, and it can promote positive, it can give nudges and positive feedback for the children to be able to sustain the hand washing behavior change. These are some of the children who participate in this study, and we are very proud to say that they really loved the interaction with the robot. And why I'm mentioning this is leading to my next slide. So I started by saying that acceptability is an important criteria for sustainability, and it is a sustainability challenge. How did we overcome this problem? We reconciled the skepticism of the teachers and of the schools in adopting robots by the enthusiasm of the children. So the pull for deploying the robots didn't come from the school management, but it came from the end users, which is the children, right? We also shifted the consumption model from a personal ownership model to a school-based community ownership model. So the robots belonged to the entire school community, right? So now this complicated what we needed to do in order to build the robot, because it was not a one-on-one interaction, but one-to-many interaction, right? The next thing was affordability. So as I told you, we had a very minimalistic design for the robot. We also kept it as 3D printable prototype so that it can be something that the schools can take up and actually replicate it using very commonly available bioplastics. We also kept the design very modular so that in case any replacements were needed at any point in time, it could be a plug and play, and maintenance of the robot becomes very easy. In terms of usability, we made the design intuitive, and we made such a way that even a layman could use the press of a button in order to trigger a conversation or in order to give some extra feedback or any. So the AI would converse with the children, but if the teacher wants to intervene and provide a customized interaction, all of it could be done with button presses. So we just made the entire design very intuitive. And in order to deal with the gender norms, we have built a lot of culturally sensitive interactions into the robot by doing various user studies with the children. So we let the children guide the entire design, and we let the children dictate to us what is it that they want to see in the robot and how they wanted the interaction of the robot to be. So with that, I will end this presentation. This being just a case study of what we have done for haptics and robotics in a much wider scale. Thank you very much.
Okay, thank you very much, Gayatri. They were 4 fascinating discussions, I think. So I will ask a couple of questions in a minute, but if anyone in the audience wants to put in questions into the chat, please do. We already have some, so I'll get to them now in a minute. So we had discussions on greener robotics, robots that can help us as a species, I suppose, combat our impact on the environment, looking at plastics and at the bottom of the ocean. We had discussions about robots becoming more efficient in factories, robots working with people, again, I suppose, in factories to reduce our energy consumption. And then we had discussions about, finally, robots in Indian villages and helping with sanitation and human health. So I might just ask a general question to the panel. All of you are involved in designing robots and working on this. What would you think the biggest help you can get, or the biggest sort of help you need, either social, regulatory, economic, or political, would be? And I'll open that up to anyone in the panel.
Yeah, if I can chip in my thoughts, I
Please.
think sustainability issue really related to both the design of the robot and how to use the robot. From my perspective, we normally is in the user stage, how to use a robot to achieve the sustainability goal is our aim. And from that perspective, I shared with you that robot working together with AI can really help a human. And to make the working environment better, that's contributing to the social sustainability. And if it's for the hardware, for the design, recycling of the materials from the robot itself, that is more for the industrial companies like KUKA or some other makers. That's my consideration at this moment.
Okay.
Yeah, just to comment here, been through the different questions and discussions that are on the panel also. Just a reminder or an important aspect is that when we talk about sustainability and robotics, sustainability has lots of variants. No, there's the environmental sustainability that I tackled. There's the economic sustainability. There's a social sustainability, and so robotics in that there is the intrinsic capability of a robot to be sustainable by itself or not. So that's the use of materials. That's how it's built, how it can be recycled. This is negative impact. That's obvious, but then it should be used for something. And if this something brings a bonus or a positive impact in terms of sustainability because we reduce the waste, because we help human disabled people, because we help young kids with sanitation, then the robot that brings a negative impact is compensated by its use, providing a positive impact in a different sphere. So it's not so easy to compare all of this. You said your question was, what help should we get, or what kind of help should we get? The issue with all these aspects in sustainability is that, except for the economic one, usually it's difficult to develop a technology, make it mature, industrialize it, and make it used if there is not a big profit to make. So these stages are the usual gaps to be filled in, and so sustainability doesn't avoid these gaps, and that's a bit the issue, to have all these systems or robots more deployed so that they can impact better or more in terms of usage. So I don't know if it's mentors, if it's public money. We already use a lot of public money in research projects, but to actually deploy it and scale it up, that's the big question for me.
Okay. Anyone else want to respond to that question about help?
Can I say a few words too?
Please.
So based on our interactions, our work on robotics and haptics, one thing we find is that technologies, in order to drive for social acceptance and social sustainability, has to be very carefully and sensitively introduced into the community. We cannot just build a robot and just introduce it in the community and expect that it's going to work, right? So it has to be designed with the people in mind, with what is needed for the people. And So the kind of help I would say is it needs greater collaboration between the West and with the countries in Asia and Africa, where there are such large sustainability goal gaps, right? And how can we drive for more collaboration where we can design, I would say, robotics and HRI, that is human robot interaction based work, which is sensitive to the culture, to the social scenarios in the country and in the different countries, and to be able to do it in a manner with the knowledge of as an interdisciplinary work. It is not just about technology, it is not about social sciences, it is not about HRA, it is about teams working together. So I think the major help is the SDG 17, which is the partnership for the SDG goals. And the more we drive across the world, I think the greater will we have success in making robots sustainable.
Okay. Baldi?
I will sum up the round of comments. First, if we have a look in what are the mega trends in robotics, and I'm just talking about mainly industrial robotics. So in the past, the megatrend was to increase the robot's size, to make it larger, to make it able to lift more weight or move more mass from one point to the next, and to make it quicker and to make it more efficient in that way. But that is now changing. Due to the last 5 to maybe 10 years, we've seen 2 more trends emerging and decreasing the requirement to make it larger, quicker, whatever. And those 2 trends are, one, the HRC trend. If you go to a industrial robots fair, you will see HRC robots everywhere. You will see HRC everywhere. And the other trend is the sustainability. And we as a robot maker, and that is not only KUKA, because I guess that all robot makers will hop onto that mega trend and will try to address both the factors of HRC and the sustainability. So it's in the interest of the makers to increase the sustainability factors of a robot, which can be the materials used, which can be the robot's life cycle up to the recycling point, and also factors like energy consumption, which I referred to before.
Hey, fascinating. I'd love to ask more, but I think I'll open it up to the audience. We have a lot of questions coming in. So I guess we'll start at the start. And this is probably for either Damien or yourself, Baldi. How do you recycle materials use in robots?
I'll take this one. First of all, we need to think about what's the robot made of. If we want to recycle it, we need to know what materials are used. And for industrial robot, most of it is actually made of cast iron, because all the structural parts of the robot, they are simple cast iron in different ways, in different manufacturing ways, but those can simply be resmelted. We also have the same that is for the gearboxes. So on average, in a regular industrial robot, we'll have 6 gearboxes, and they are also just made of metal. So you can resmelt them. You will have a lot of internal cabling, which is in its basic components copper. You can recycle that very simply, very easily. Then there's some very small components of plastics, like cover caps and stuff, but we're also able to recycle plastics. Then there are motors, and there's specific ways to recycle motors, because if you go in the in-depth of the motors, there's rare earths and copper windings. That's a complex topic, but there are ways also to recycle or reuse in the best way possible the materials used in motors. And at the end of the day, there's also to some degree, there's oil or another form of grease in the robot. But all of these components, there are ways to recycle them in a very easy way that are also very broadly used already. So recycling a robot is nothing special. You just need to dismantle it into its core components, and then you can reuse 99% of its components.
Could I just ask, are there standards, industry-wide standards, demanding that you aim for recyclable robots, or would it be in the economic interests of some manufacturers to develop robots that can't be easily recycled? So would there be those problems of free riders when it comes to recycling in the robotics industry?
I'll take the question. It is in our interest to develop robots that have a maximum lifespan that can be reused until its final motion, but once it's done, it must be able to be recycled, because otherwise we would be wasting precious material. And this is something that we have both the environmental as well as a financial interest to make it recyclable.
Would you say that's held across the industry, or do you know? Maybe you can't answer that question, Holly. I don't know.
I can only speak for the Orange brand, but we have that interest, yes.
Yeah.
I would say that there is also a second-hand market on industrial robots that can be used when, I don't know, a manufacturing of car factory changes its line. They can provide the robots for reuse. The mechatronics will have a longer lifespan. Usually the issue there is that the electronics controller is on the old generation. So there is still, and here a hint to cook our ABB, to be able to have an upgrade of the control system so that we can still use the mechatronics of old robots that would expand their lifetimes for not so aggressive applications, but to be able to make an upgrade, that would be a good thing to increase the reuse of these systems. And then there are robots that use carbon fiber that are not recyclable. I don't think that there's real requirements anywhere. Some lighter robots, they use plastic shells also, covers. At the end of the day, it's lots of plastics, metals that I agree with Paul, they can be disassembled and recycled separately if people take care of that. But this design for remanufacturing, design for recycling, it's just one more object in the world that there is no regulation to actually request that only recyclable materials or biosourced materials can be used. There are also examples of robots made of wood. You can check French people in Nantes, they made robots made of wood. So there's all things possible.
Okay, I'll go on with some of the questions. What is the penetration of such robots, I think environmental robots, broadly speaking, in world markets? Do we have comparable data across continents at all?
You will have lots of data of worldwide sales and deployment of robots for industrial robots, for a service robots, but in general scale, that's done by the International Federation of Robotics. And here they have lots of data. Something specific for the environmental use or the more broad sustainable use of robots, I'm not aware of that. I would give my 2 cents that there are very, very limited applications. Where they would have a more massive deployment would be on the sorting of packaging in the waste treatments. And here you have a few brands, companies in Europe, in the US, in Canada, everywhere, that start to deploy robots also for the sorting of waste on the belts. But I would say that it's a very small niche at the moment, and lots of demonstrators, prototypes that do not yet scale up due to the cost of these systems, requirement of industrialization so that they can be widely deployed. But that's my 2 cents.
Let's go on. How can we become more aware of balancing the positive impact and possible negative impacts of robots during the development and initialization of or installation of robots? Anyone want to take that on?
Raise consciousness on people using robots just as people using cars or people using the commute using trains or bike. I mean, if you are sensitive to these topics, you might ask yourself the question. If you're not, you'll try to go to full efficiency, whatever the cost. Maybe the cost of energy could be one topic to actually start the enlightenment or the discussion. Trying to bring these companies or integrators deploying these robots to actually look at the economic impact of the energy use if it's not optimized. I was mentioning Paul D on their research. Otherwise, I think it's only either a legal thing that come as a request, or it's just on the conscience of the users.
I mean, would it be helpful if we had regulations saying that robots had to be, I don't know, have solar panels so that they could generate their own energy? Would it be helpful to have regulations, say in the EU, saying that we did have to use recyclable biomaterials or have supply chains that were in some sense ethical? Or would the industry be very much opposed to such requests, do you think?
At this point, regulations, industry is always reluctant to regulations because you need to change something that in your opinion works perfectly good and there's no need to change it. Do we require regulations to incorporate a certain amount of recycled materials in, say, the robot structural parts or something? Well, no. That's from the industrial point of view, because it really doesn't, from my point of view, it doesn't matter where you reuse the material. If it's resmelted and then recast into another part of something, the crucial information or the crucial part is it has to be recycled. What is made out of it afterwards, if a new robot is made out of it, or a part of a car, or your drink can, or whatever, from a global point of view, that doesn't matter. So do we actually need regulations? At that point, I would say a clear no, because all of the robot companies, they have the inner drive, they have the inner will. We want to be economically sustainable. We want our products to be as efficient, as good in use, and as recyclable, sustainable, whatever you want to call it, as possible. Because for us, this is a kind of USP. So we can sell our products better if they are more sustainable. So we have the urge to do it.
So there's a market incentive.
Yes.
Okay, fascinating. A question for Gayatri. Which disciplines were involved in your background research?
So we really do interdisciplinary research. So our research is on robotics, on human-robot interactions, and social sciences. So, you know, we have our robotists actually go to the field, spend time in the villages of India, and really sit with them to try and understand the solutions that we need to develop for them from a place of empathy and compassion. So it is not like, you know, we know what you need and this is the solution that is best for you, but really do a community, involve the community in the development, in the design, hear them and take their inputs and feedback and then develop. So this work that I presented is on social robots. It's not like the industrial robots, which are really something which probably the community may not be able to contribute much, but at least in the domain of social robotics, especially the kind of interactions they want and the kind of expectations they have can be built if we co-design the robots with the community. And that's why we blend in researchers from different disciplines and put a team together for the work that we do, so that it is, it's more holistic in its solution.
Would you, we have another question. Would you be able to tell us how and where you produced the robot and at what cost? And did you, at what cost you produced it and where you produced it? Gayatri.
So, as I said, for the social robots, our designs are 3D printable, right? So we try to keep it minimalistic. Where we produce them is any fab lab or any place which has some kind of a maker space, including school maker spaces. We can 3D print and build them. It takes about 2 to 3 weeks in order to assemble the robot that we call as Hakshi, which is for hand washing. So the goal is that the community will be able to find local spaces and local areas where they can produce the robot with the blueprint that we give them. So the software is not produced by the community. We tell them what to do. but the actual hardware is a lot of the things we keep it off the shelf and which can be locally built in any kind of a makerspace.
Okay, fascinating. We have another question for yourself and Lihu. Would you suggest that in all cases of human-robot collaboration to increase sustainabilities, engineers should be collaborating with HRI and in particular with anthropologists, sociologists, and ethicists? These are specialists in analyzing practices and experiences that matter for human well-being.
Absolutely. I think that, when people from different dimensions come together, different specialities, there is a lot of richness that they build based on the best practices. And we think that innovation really comes only when there is this, as I said, this interdisciplinary work of anthropologists, sociologists, robotics, not really looking at their own fields, but looking at the problem and trying to see what is the best way to address the problem in a sustainable manner. So yes, absolutely, that is our philosophy in the work that we do, and yeah, we believe that is the right way forward.
Lihu, would you have any thoughts on that, on collaborating with the humanities, with ethicists, sociologists, and so on?
Yeah, my background mainly in the industrial setting. We do not work on the social robotics. For the industrial robots, there's a need for using robots to help human operators. Normally, human operators' working conditions are very tough, especially in bigger component assembly or final assembly. Using robots to help human can reduce the workload and increase the quality, because the robot is really powerful and with a higher accuracy compared with a human, but a human has the flexibility. That's why there's a need for human and robot to work together. In a sense, if a robot is used properly, we can also save electricity as well through the proper planning. And for the human side, the sustainability in the social dimension is huge and reduce quite a lot of work-related disease or back pain and so on. So we consider that human-robot collaboration for the human is a must in the future.
I've got a sort of question, maybe mainly for you, Lihu, but it might also apply to you, Gayatri, about responsibility, particularly if there's an accident with someone controlling a robot using a brain-computer interface of some sort, who would be responsible? And similarly, if someone was nudged to do something in a village that caused an accident, have you thought about how we might ascribe responsibility in such scenarios? Is there much there?
Yeah, if I can answer first, this is a question we normally encounter. Currently, there's no standard. Even for human-robot collaboration or collaborative robot, there's no ISO standard yet. There's a technical specification under development. Without ISO standard or equivalent standard, it's difficult to trace back to the responsibility. Right now, it is still on the human, no matter it's the designer for the robotic cell or the user of a robot that holds the responsibility. I don't think the robot maker holds the responsibility at this moment. It's more about practical use on factory shop floor. The user needed to receive proper training and understand all the possibilities it may happen. At the same time, the cell designers needed to secure double or even triple security measures. The last one is based on the emergency stop. But if we're talking about the brainwave-driven robot, Normally, in a panic situation, it is possible to capture the surge of a brainwave in high frequency. And that one can be used to trigger emergency stop to protect the human as well. Okay. So that's the current responsibility. If we have a clear international standard, that could be a guideline for the business owner to set up a proper policies how to use a robot, and also associated with insurance policy as well.
Right, and in social robotics, ethics is something really important. So when you talk in terms of responsibilities for failures, that is definitely a very important consideration. And that's why whenever our work is on deploying robots, it is not with the aim of deploying the robot per se, but to first build a relationship of trust, mutual trust, because when we are solving problems for a community, and community is part of the solution to the problem, then it is not about who is responsible for either things going right or wrong. It becomes a community ownership of the particular problem, right? So yes, mistakes happen in the sense that robots can get hacked. There could be errors or socially inappropriate conduct from a social robot. These are definitely there. But when we work carefully with the users, we find that users are quite forgiving, actually. They are not here. They understand that technology is actually an enabler. Technology has lots of positive sides it can bring. And the goal is to try and create something that works for everybody. It's not about trying to be a crab and pull everything down saying nothing is going to work. Nobody wins in that situation. So we believe that when you bring the social mindset in such a way that more acceptance is built for robots and technology, then the issue of who is to be blamed doesn't come up in that way. It is a community problem, right? And it is not one person's, it is not the robotist who is at failure, it is not the designer, it is not the person who deployed the solution, but it is a collective problem and it is a collective ownership. So that is our approach to tackle this particular problem.
Okay, thank you. I will ask, I suppose we're getting towards the end. We have a very practical question for you, Damien. How do you select a seabed location for waste extraction? And what do you do with the plastics and tires collected? What is your recycling method?
Well, so this development is done within the European project Maelstrom, H2020 Maelstrom. And we have lots of partners. We are developing it in the Venice area in Italy. And here we have two partners, the CNR ISMA, which is a biological research lab, and a NGO, Venice Lagoon Plastic Free, that are actually identified hotspots. So these are areas where there is lots of waste, that is known to have lots of waste. The visibility in Venice lagoons, you might imagine that they're very, very bad. So what we do to be able to actually see the things is a prior scan using sonar sensors. So we make a map of the seabed, and here on this map, we can identify the larger objects. And so that's where we drive the platform above them, and with a cable robot that has cameras and other sensors, we can go down and detect these objects, also the smaller ones, and then we pick them. But so the hotspot detection should be done prior to deployment and the use of the system. it's not a system that should be deployed everywhere where there is no lots of density of waste, because obviously it requires lots of transportation and gasoline to propulsate and so on and so on. So hotspots are the key topics, and they should be done prior with sensing technologies. And what we do with the waste, that's actually also in this European project a big part of the project, to actually take these wastes, recycle them into new products. So here there are different partners: GES Recyclings, McKean, Syntoil, and Technalia also. So we do pyrolysis of the waste. We do in Technalia shredding, and we will create composites based on the plastics collected, with also fibers collected from recycling of windmill blades. And GES Recycling, for example, they take all these very hard to recycle composites or plastics that cannot be melted. They smash them on panels that can be used for, I don't know, just like in the kitchen things, or on the floors. They do ties on the beach. One of the other partners, the Great Bubble Barrier, for the rivers, they will use that to make a container for their own system. So that's taken on the edge of the project. It's low quality plastics and waste, so it's difficult to get value out of it. So we try to get enhancements and bring them up on higher value products so that it can be used for people.
Well, I think that's, I mean, it would be great. It's great to hear about someone addressing our plastic problem. I think that's a very positive note to end on. We're going to turn on the sort of outro video now in a minute, but I would like to thank the panel, Poldi, Damien, Gayatri, and Lihu. I hope I got to as many questions as I could. I think we answered most of the topics, and I apologize if I didn't get to any specific questions. Thank you all, and over to you, Guillaume.
So thanks a lot, Fiacra, for this excellent moderation, and a big thanks to all our panelists, Damien, Lihu, Poldi, and Gayatri, from me, as well as to all the participants for this very interesting and engaging discussion. And now we encourage you to check out the AI for Good program online to see more robotic sessions that may be of interest to you. And basically now it's the end of this section, and we'll have a couple of minutes of networking in the AI for Good neural network with the panelists and participants. So see you in a couple of minutes. And now I give you the floor back to Anna for the closing information. Thanks a lot to everyone. Bye-bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.
you.